All right, I think we can start. So, thank you for joining us today, and welcome to AryaXAI's webinar, Inside the Black Box Interpreting LLMs with DLBacktrace. We are really excited to have such a diverse and engaged audience from across the globe. And as we deep dive into DLBacktrace, it's the AryaXAI's latest contribution to the explainable AI ecosystem, and something that has become more important than ever in the era of AI driven decisions. I'm Sugun, and I'll be your host for today's session. Here's a quick look at the agenda today. So, we will have a short introduction to AryaXAI, what we do, and why this work matters. And that will be followed by the main presentation. And finally, we'll wrap up with a Q&A session, so where you can ask any questions that you may have. So during the session also, if you feel that there are any questions, please feel free to drop them in the chat box below, and we'll take them up towards the end of the session. So to take through this work, we are honored to have Pratinav, who's a research scientist at AryaXAI and the author of DLB library. So let's dive in and let's get started. I'd like to invite Pratinav to say a few words about AryaXAI, the team behind this initiative, and the broader vision driving our work in AI explainability. Pratinav, over to you.
Yeah, thanks a lot, Shagun. So, hi everyone. Today we'll be talking about DL backtrace. So, DL backtrace is a method through which you can do model agnostic explainability. And in today's session, we'll be focusing particularly on LLMs as well as the fundamentals of DL backtrace. So, before this, hi, I'm Pratinav. I currently work as a research scientist at AryaXAI alignment labs. I'm currently working around AI interpretability, alignment, and other real-world tasks which we are dealing with at AryaXAI. So starting on this, what is AryaXAI? So AryaXAI is a ALM, like AryaXAI alignment labs is based out of Mumbai and Paris. So our main goal is to how you can solve AI interpretability and alignment. The reason being how they are very important in today's world, and with all these regulations coming up in different parts of the world, it it leads to further more questions how you can actually interpret different AI models which are coming up every week, and how you can build on these new techniques so that you can ensure the models which you're using are safe to use as well as well aligned. Our current approaches works around building new techniques to solve these problems, how you can work on open source tools so that the industry has tools to solve certain problems as well as have enough tools on AI safety. Alongside that, we also work on open source tools. We have two tools, which is DL Backtrace and XAI Vats. Alongside that, we also collaborate with the academic and research labs. We're also hiring for a couple of positions around research as well as software development and more. If in case you're interested in our vision, please feel free to contact us or me. So yeah. So coming with this, like, what's the main problem in AI? I would say, like, every day you have different teams coming up. You have different, I would say, organizations creating domain-specific models. However, with the I would say the huge impact it is causing number of people who are actually using these models. The problem is there is very the especially in mission critical tasks, let's say in finance. Uh, the usage of AI is very sensitive because it can lead to quite high monetary impact, as well as in other domains as well. There is a very high impact on using AI, especially let's say in medical, let's say in manufacturing. It can lead to large scale impacts, and it is very critical. And it can lead to other problems as well if you're using it in everyday life, which is mostly around, let's say, manipulation and other stuff. And the reason why all this is important and why we are working around this area is there's nothing much which has been done around AI safety and alignment, making it a very important problem and something which needs fundamental research to solve. So again, building a model is easy, but accepting, or you can say making a model acceptable, is hard. You can every day create a new model with new data, but how do you ensure that it is transparent and it aligns with the compliance of AI in different countries? So again, with AI regulations and coming with that, how do you ensure that model doesn't fail, or if the model fails, you are informing the end users about it? So anyway, like, I would say it needs acceptance from all stakeholders, which is if you see in terms of financial operations, which is head of products, operations, how they can trust AI, how you can make AI models which so that it satisfies your risk teams, which is making the AI decisions fair, ensuring they are transparent. It shouldn't be random, like it should be deterministic. So for every similar data point, it should have similar results. It should pass all regulations, especially the government regulations, so that there is no bias. And the customer should have some sort of, I would say, assurance or confidence on the AI models, whether decision is actually correct and it is quite fair. So again, like if we know all this, why there's a problem of AI explanation or why there's a problem of AI alignment or interpretability. The reason being there is methods to explain different models, but they are not correct, or I would say they are mostly sometimes wrong explanations, which creates distrust among different users, which we saw the previous slide. And another problem being they are not acceptable in many cases because a lot of these models are black box, and which makes it very hard for a method to explain it. And the secondly is very hard to debug the problems with the explanation methods. And in current times, there is a lot of maturity, which is in AI regulation and governance. In Europe, again, you have a traditional, or you can say a milestone-based AI regulation act, which has come up and will be in picture starting next year. And US, you have a lot of regulations coming up around AI in different countries. Let's say in Canada, in China, you have a different sort of regulations. In India, there's something which might come up in the next few months. So there is I would say, uh, I would say is there is a, I would say realization among different governments that with the use of AI in everyday life, there is regulations and governance through which these AI models should align with. So this comes up with the basic problem in AI models, which is the black box models. We know, okay, these models works great, but how do they come up to these decisions is something which is problematic. The reason being, so all of these are based out of something called a neural network, and with I would say a million parameters, or I would say a lot of operations which is happening inside these models, it makes it black box to interpret. You have a lot of explanation methods right now, something which is model agnostic called LIME and SHAP, something which is gradient based, GradCam integrated gradients. But again, like all of these doesn't work on all models or all tasks. They are very specific to a task and the model architecture. And the second most important thing is how do we evaluate these methods is something which is not very clear. Like there are certain metrics, but there is no unified standard around this. So why is this whole problem coming up now? Why not previously, let's say 5 years back? The reason being with the increase in, I would say, complexity of these models, we are unable to understand the models exponentially with the increase in complexity. And hence, with how good the models are being, we are unable to again have any understanding of how these models work. So this leads to questions like what are the current explanation methods? You have visualization methods, you have something called, I would say, perturbation methods, which is quite popular in the domain, where people actually work around different perturbations or try to trick the model to understand how the model is working. You have approximation methods called LIME and SHAP, which is quite popular, which is basically surrogate modeling. You have tree-based methods, which is again tracing back to traditional ML, and why people are quite hesitant, especially in, let's say, again, the high stakes tasks, let's say in finance and other domains, to move on to deep learning is because with tree-based methods, you are able to understand how a decision is being made, which is explainable in itself, but this cannot be translated to deep learning models. You have attention mechanism, which people nowadays try to use in order to explain their models, but it cannot be directly translated to explanation. Then you have another domain of joint training, which is making the model learn explainability while it's learning the task. So that is again a different field in itself. But all of these have their challenges. They cannot be expanded to, I would say, a particular domain or all domains. They are not model agnostic. They are not applicable to multimodal inputs, which is, I would say, the future in next 1 year. Like most models will be multimodal, and a lot of models are multimodal at this point. There is no stability of these explanations, and they are not true to the model. So again, it creates a lot of problems if we want to have like a unified framework to explain all these models. So with this, I'll quickly go through each of, I would say, commonly used methods. So you have LIME, which is again a surrogate modeling method, which is probably used the most in explanation these days. Again, and similarly, you have SHAP, which is again based on Shapley values. Both of these are very popular surrogate-based methods which people use for tabular data, especially. But the problem in these is like you can work around these and you can get certain estimations of how or what features are important for your model. But the problem is when you go on a case by case basis, like these doesn't make sense. So your explanation should be actually based on the feature, or you can say the input instance, instead of just certain number of features, and they can be easily fooled with something called like a lot of perturbation based attacks. So that's a problem with these two methods. Then you have GradCam, which is very popular in computer vision based methods, but can be just be applied to, I would say, classification based tasks. You can try to apply it in segmentation, but again, you cannot move beyond that. Integrated gradient is something which is very popular. It has been now been used in Llama and other models as well, but it cannot be trusted. It's very dependent on the baseline on which you are creating these explanations, and it can again lead to, I would say, large computations because you have a lot of gradients when you create like a good large model. So again, it might work along a lot of models, but it's very sensitive to the baseline which you are choosing. So it's not a very stable explanation method. Smooth RAD is again on the similar lines. It's mainly been used, I would say, is computer vision, but again, you can extend it. And then you have LRP. LRP is something which is based on backpropagation. So what it does is it tries to redistribute the model prediction back through the layers to assign relevance. So again, this is a method which can be applied to different, I would say, model architectures and tasks. However, it is very computationally complex, and again, it's very tightly coupled to neural network architecture, so very hard to scale. And so yeah, this comes up with again the same problem. So there is a black box problem in AI, and how do you solve this model agnostic explainability? So in order to do that, we came up with DL-Backtrace, which is again a model agnostic explanation technique. By model agnostic, what I mean is you can apply this to any model architecture, and you will be able to understand how your model works and how your model is making a particular decision. So again, why did we come up to this? Because you already have LRP, which was there. The reason being, like, again, we wanted something which is extensible, and we wanted something which is, I would say, just now depends on the rules. So in LRP, you have certain rules based on which all the computation is being done. And our method comes up with a single rule which can be applied to all layers and is quite stable. So our main intention is again like the algorithm for explanation should be network, like independent of network architecture, independent of the task. It should be only based on the model weights which the model has learned and the input data. And it should basically have contributions of each particular unit in the model. So you can understand, okay, how much each per component is contributing, and based on that, you can decide the importance. So again, how does this work and why the name DL backtrace in the first place? So in a neural network model, you have a model architecture like the blue part, which you can see, and you do a forward pass and you get the output. After that, what happens is in backpropagation, you just backpropagate it based on gradients and you update the weights. In similar manner, what we do is we create a relevance score based on the output and we backpropagate, or you can say backtrace back the relevance value based on the rules which we have created. And based on these weights, we are trying to assign relevance value to each of the model layer, or you can say operation. And when this happens is we ensure that it's similar to, I would say, a good example can be Kirchhoff's law, where the relevance is kind of reserved between all the operations. So you will get an explanation map which is similar to your input data. So a good example can be the one which I show in the next slide. So again, you have your data, you do your feature engineering, you again pass it to your model gives the output. Then what you do is we are just observing the layer-wise output. And based on that and the weights, we are trying to compute a relevance value, which again which again we try to backtrace it, and hence you get something like this, which is similar. I would say attribution map can be one of the ways for some people, but it's more of a explanation of which areas of your network actually impacted the decision. And while we are doing this, we also give you the relevance, or I would say importance, of how important each layer of your network is. And based on that, you can again do for future tasks. So I will come to that in the later part of this webinar. But again, how does this work is you have like a single, let's say a single layer, which is can be computed as y is equals to sigma wx plus b. So in this wx, what we do is we separate it out as xp and xn, where xp is the positive contribution part and xn is the negative contribution part and b is the bias. And based on that, again, we try to compute the relevance. So I'll come to that part in the next slide. But again, like just a refresher of how this works is, again, we start from the back. We try to move around, I would say, layer wise in a breadth first search manner so that all nodes are covered. And for each node or layer, we try to assign relevance. And at last, you come to your input layer or the input uh, data which you are giving, and you get a relevance value, or I would say explanation for that. So again, we have two modes of doing this. One is a default mode and one is a contrastive mode. So getting back to what we had y is equals to sigma wx plus v, where you can separate wx as xp and xn. So once you have that, let's start with the default mode for a better understanding. So in default mode, what we consider is your total relevance tj of a layer can be segregated out as xp, xn, and b. So this xp, xn is like the positive contributions, negative contributions, and contributions of the bias term. Okay. And based on this, what we do is once we have our wx and your xp is again like the positive contributions which we talked in the earlier slide. So based on that, we try to calculate the relevance based on certain conditions which we calculated. And once we have the relevance of each node, or I would say based on the layer type, it can be each filter, each run. What we get is a combined relevance value, which can be like a total relevance based on all the operations. And it comprises of both of negative contributions xn, which we talked on earlier, and the positive contributions, and hence we get like a total relevance value for a particular layer. In a similar way, what we do is we also have a contrast mode where again you have a total relevance, but we segregate it out based on the positive contributions and negative contributions. Like if the negative contribution is greater than the positive contribution, then we compute it in a different way. And if the positive is less than negative, then we compute it in a different way. So that we are able to understand, okay, what contributed positively to your network and what contributed negatively to your network, and hence we compute the total positive relevance as well as the negative relevance at a particular node. Again, so why is this important and why do we just come up with the contrast mode? Again, like we could have just stopped at default mode. The reason being, in certain scenarios, it's very important to see like what was the positive reasons on which region is being made, and what was the I would say regions, or I would say the point at which the negative decision could have been made. So a good example can be in the segmentation task, which we'll see earlier. But I would say a good example is something like a distinguished boundary based on which decision is being made in segmentation. So that can be a good idea. But that's the reason we came out with the contrast mode as well. And with this, there's one more addition which we did was for attention layers with all LLMs and BERT, and I would say all the attention-based mechanisms of models which are coming up in today's time. It's a very, I would say, necessary step. So for attention layers where you have, I would say, a soft attention as a multi-head attention, which can be represented as something like this. You have query, key, and value. So what we do is we try to compute attention based on query and value and query key and key. So it is inspired from attention LLP paper. And hence, based on that, we try to compute the relevance of query, key, and value separately. And for total for the attention layer, you get like a summed up value, which is just for the attention layer. So this is what we do for the attention layer. With this, we'll move on to the benchmarking. So once we had this method, like again, how do we know if this method actually works? We try to benchmark it for three tasks, which is around tabular, image, and text. So for tabular, we had lending club data. We had two metrics, MPRT and complexity. We'll come into that in the next slide. For image, you have CIFART and multi-class classification. For text, we use like a pre-trained BERT for sentiment analysis task. Uh, Again, so let's go to the metrics part first. So For tabular metrics, which we used MPRT and complexity, MPRT is basically measures if how much perturbation can be applied to the input before it changes the model decision significantly. So this is one area which we tried, and second is the complexity, which measures the model explanation, like how different or how I would say fine-grained your model explanation is. So these are two things which we measured. The second, for image, we use faithfulness correlation, which measures how your explanation aligns with the model behavior. Again, it's similar to like a perturbation-based method, which try to have like a correlation between your feature, like how important certain features are and how does the model decision change based on perturbing those particular features. Next is pixel flipping, which is again similar, like it finds out important features, we try to perturb it, and then we see if the model decision changes. So apart from that, we have text metrics, which again perturbation based. Like we try to attack the model on particular features which it shows to be important for a explanation method, let's say backtrace, and least relevant features, and then we try to create a graph out of those performance and basically I would say no network confidence, and then we find the area between them. So again, coming back, how do you do all this is again very simple. You just, I think for the free version, what you can do is you can pip install a library. You can just pass the model. You'll get all the relevance values, and based on that, you can try things out. Basically, interpret the model and do stuff. And if you want to quantify it, you can use our library as well, which is XAI evals. So coming back to this, so for the image task, which was CIFAR 10, again multi-class classification. We got like quite good scores for faithfulness, correlation, max sensitivity, and pixel flipping. The evaluation we did was 500 samples from the test set. And yeah, so what we observed is like there is quite good value in terms of faithful correlation, like with perturbation, even with that when we are using backtrace as the explanation method, there is correlation between perturbing the most important values and the model prediction. Similarly for sensitivity and pixel flipping, which gives us an idea, okay, the model is working actually good. Illustration, so this is the model architecture, but coming back to the illustration, if you can see it visually, it gives like a very good idea to us when you see this. For methods like let's say GradCam, it gives high importance to everything, so you're not able to distinguish actually if the model made the current decision or not. For some it's actually blank, but for backtrace, if you see, it actually focuses on the edges and parts of the model based on which the actual decision is being made. So if you see the horse image, it's actually focusing on the edges part instead of just the body part. So it's actually seeing the shape of the object and then making decisions. Similarly, for the image front, we again tried out with segmentation and object detection. For segmentation, again, these are the again ablation task. For segmentation, we use CleaningDB and CamVid datasets. And here, I think it's a very good example of the contrastive mode, because if you see here for GradCam, it's again focusing on the inside and giving more relevance, and you have certain areas which is excessive. But for backtrace, again, you are focusing more on the edges or the actual point where the decision is being made. And if you see the positive backtrace, again, it's the same. For negative, it's just the edges, because those are the points on which the decision was being made to be negative. So it's not segmenting the areas outside of this, hence you're just getting relevance of this particular part. So for similarly for object detection, we use like a very small model. And again, if you see GradCam and other like GradCam, then it's very blurry. You're not able to get any fine-grained details. But for backtrace, that's not the case. You're actually able to get very fine-grained details. And again, you can use this to improve your model and in various use cases. With this, we'll move on to the tabular data. So tabular, we use like a very simple MLP model, or you would say a very simple neural network model. And the performance of the model was actually quite good. It's scored around 0.92 on the lending club dataset, on the full dataset. So we just conducted this study on like 1024 samples, because all these metrics take a lot of time to run. And what we see is like for MPRT in all layers, Backtrace is actually performing way better than Lime and Sharp. And for complexity, while the score is higher, the reason why we say it might be good is because it gives you fine-grained features. So again, that's why backtrace is much better on the tabular front as well. And if you try to do it yourself, let's say on the free library which we have, what you will observe is For Lime and Sharp, the problem is, let's say I would say for Sharp, it just selects like, let's say top 10 feature, or I would say for Lime, it's more of like it selects top 10 features based on the training distribution which you give, and it just gives very high importance to those features. For Sharp, the problem is it gives very importance to almost all the features. So again, it doesn't make sense to use both of them because you want to be very specific to a training sample and you don't want everything to be very high. Again, then it won't give you any value out of it. So backtrace is better in both these fronts. I think you will test it out, then you will see it for yourself. With this, we come to the BERT or the BERT model. So for BERT, we use like a text attack pre-trained model on a Stanford sentiment tree bank dataset, basically sentiment analysis for positive and negative. And it's like a pre-trained model which we used. So for our experiments, what we observed is while backtrace is not the best in this, IG was the best, but backtrace performed quite decently, both for MORF and LERF task, and the delta was also quite decent. Hence, if you see the performance for different words, let's say this is an illustration. So what you will observe is for backtrace, you're actually getting good relevance values and you're able to use it to actually understand how things are performing. Whereas for other methods, while they actually did perform better in the metric, the values are very close and very small. And hence, when you're using it in actual life, it might have some issues because of the closeness of values. So again, like what can we again conclude with all this? So you have in tabular models, you have superior MPRT compared to Lime and Sharp, although you have higher computation complexity, but it can be I would say it's more reflecting on the granular explanations. For image modality, again, we are best in all three methods, and it's I would say if you see real world use case as we saw earlier, it's much better to use when you're working on high stakes tasks because you need fine grade explanations, or I would say importance of which area your model is actually looking on. For text modality, IG is again better based on current metrics, but backtrace, we are working on it. We have few results which are good. So, and it's actually able to show it can perform meaningful explanations. So that is something which you can try on. With this, we've also tried on different tasks in text as well. So we tried on T5 Bird, we tried on Llama, we tried on Con 1D, which is like a very small model for multi-task classification. So this is for Con 1D. If you see like compared to Lime and Sharp, here the cases are reversed. We just focus on very small words, whereas Lime and Sharp basically, I would say colors, or I would say have a importance in almost all the words, whereas here we are actually looking at certain words based on which the decision is being made. So that's the case. Whereas similarly, if you see for this is like a LSTM based Nexus prediction model. So I would say, let's say science and technology, this is like a news headline. So again, you're focused on actual words instead of just focusing on everything. Similarly, for a T5 model where we are actually doing translation, you are able to actually see how much importance each of your generated token, for each generated token, let's say what was the most important token based on which it produced that token. So that is something which you can observe and can use while you're tracking sequence to sequence translation. Similarly, for the Llama front, again, you can actually use, I would say, to see okay which area was based on which the generation actually came into the picture. This is like a sentiment analysis task which we prompted where we are actually classifying a test into negative, positive, and neutral. So you can see okay it is looking actually into the task. Okay, so you have to classify text, neutral, positive. All of these are very high relevances. Then it's actually looking into the areas and not actually looking to the stop words which are not very relevant. So again, it's actually looking into areas based on which it's making the decision. So with this, we'll move on to the next part, which is the notebook walkthrough. I'll reshare my screen. So we'll just go through few models around Llama 3.2 and a few mixture of expert models like OLMOE and JetMOE. So just give me a second and then we can start again. Just one second. So yeah. Okay, so let me reshare my screen. Cool. So let's start with JetMOE. So JetMOE is again like a mixture of experts model. So what you can do is it's again very simple. You just load the model and let's scroll through it. And again, you have something like uh, let's say you are giving a token, provide a function that calculates nth Fibonacci number. And what we are doing here is something like, okay, how do we compute the relevance? So we just compute the relevance using backtrace.eval, which is similar to what you have. And then you are actually able to see what is important. So we are seeing, okay, provide a function that calculates the nth Fibonacci number. So it's actually looking at each component. And based on that, if you try to see, so okay, function is something which is important. And then nth is important, Fibonacci is important. So it's actually tracing it back to the important text based on which it's generating the token. So for each token, you are able to see that. And if you also get something like this, which is like a, I would say, a relevance graph or importance graph. So for each layer, you are actually able to see how much important it was throughout the whole process. So each fully forward layer, each self-attention layer, and using all this, you can actually do a lot of stuff. You can actually work on optimization. You can actually move or prune out layers which are not very important. And hence, it's actually something which you can use while for optimizing your model, for aligning your model. And similarly, you can get something like this, which is there in our in-house product. So if case you want a demo, so bef Llama and OLMO is not in the public source version, but if you are interested, feel free to reach out to us. Details will be provided at the end of this webinar. So again, you are able to actually see what for each layer, how much the relevance is. And alongside that, you're also able to see for token. And since it's like a mixture of expert model, so what you can do is you can also see for each of the experts. So this is for, I would say, across all transformer layers, what we are seeing the relevance of each token. But you can also do it for certain layers. So for each particular layer, what's the relevance? Then again, for each layer wise, this is something. Then again, you have for token, so or expert. So here you have 8 experts. So for each expert, you are able to see how you can trace back the relevance value or the explanation, which particular expert is important, which is not layer wise, and hence you can use all these information. And this is again a good example for so which expert is actually important in the decision making for that particular sample. So let's say if you're doing like a domain specific task, so you can prune certain experts and just keep the other set of experts for that task, and hence will make your model very lightweight. Similarly, let's say for Llama, Llama again, you can do the same thing where I would say let's complete other OLMOE. So again, for OLMOE as well, you can do something like this. For Llama as well, you can do something like this. So that's a few things. Okay, 1 second. Um, yeah, so let me share. Yeah. So let's say for Llama, you have something like this, which is you have like a sentence where you are trying to classify. Again, this is something which we saw earlier, the sentiment. So you have all these processes where you're actually going into each token, and then you're able to see, okay, which one is important, which one is not, and you get all a graph like this. So you can understand, okay, if is your attention layer in the Llama important, is certain feed forward layers important, and based on that, you can actually see it for yourself, and you can prune the model, you can actually optimize the model, and you can again have a transparency of which layer is actually important. And with this, you can also see, okay, which one layer is certainly important for the model. So that is one thing. Apart from that, let's say for JetMOE, we have something like this, where again you compute for each of their expert. And similar to the previous model, you are actually able to see which expert is important. Again, like it's a similar sentence, so you can see that. And yeah, for each expert, you are actually able to understand how your graph is working, how your model is working. So for, let's say for this particular sample, we see, okay, certain layers are not very important. So we can just prune them together and make our model much better. And similarly, it's for different layers, different experts, and you can actually do a lot of stuff on the alignment front. So this is how everything can work with Backtrace. So yeah, with this, let's come back to the slides. 1 second. So yeah,
Meanwhile,
cool.
if anybody have questions from the audience, feel free to drop them in the chat box below.
Sure. Yeah. So again, this is how everything works. So you have your data, you have feature engineering in any modality, you get your model. Uh, so with model, we can get the layer-wise output, and again, we calculate relevance and get the explanation back. So why backtrace? Again, why not, let's say, something like a LRP or something like GradCam or IG? So again, as you saw, you have like a full network analysis, which you can do with backtrace. You can understand what's the certain biases in a data which you have. You can incorporate, let's say, uncertainty. You can get feature importance. You can have the versatility because again, you have local level feature importance and understanding of a network for, let's say, a certain subset of features, and you have a global level understanding of the features by comparing, like, putting all of these together. And again, there is the efficiency because again, there's no repeated inferences because it's a deterministic method, it's not perturbation based. So that is something which you can do. You can just get all the explanation back in a single pass. However, there are some limitations, which is the computation cost, which we are right now scaling. And then again, there is a model access required. We need your model weights to actually work. We cannot work on black box APIs. So that is some limitations. Coming on to it again, like Backtrace is novel and robust method. It's clear, consistent, and it actually outperforms other methods in robustness accuracy. And with this, we are trying to promote responsible AI, and especially mission critical tasks, because Backtrace is deterministic. It's not probabilistic, where it can change for every instance. If you give the same model and the same data, it will give the same exact value. So what we are actually working on in future is expanding its applicability. So currently in the free version, you have a limited access, but with the in-house version, you will have much more number of models, and we are making it model agnostic in a way you can basically have any PyTorch layer or any TensorFlow layer in your model, and you can just use that model checkpoint or model architecture and then just run backtrace on it locally on our platform. We are trying to reduce inference time as well, so that you can actually do it on real time alongside your inferences. So the speed will be very similar. And we are also exploring model optimization, as I mentioned. So with this graph, you get all this information. So how do you use it? Actually help your model, and how you can use it for safety and auditing, especially. How can you use these models to understand, okay, if there is certain, I would say, spike in relevance value or explanation of certain layers, so can it lead to hallucination or failures? That is something which we are studying right now. And lastly is the model auditing. Like, can we use these values to actually ensure that your model is ethical and aligned, especially for financial services? That are the few areas which right now we are working on, and we'll be sharing a result soon. So with this, I'll be concluding my web session. But yeah, do if you have any questions, please message us in the chat board, and you can actually go through our preprint. We have open sourced everything. So the paper, right, the backtrace paper has been accepted at IGCN conference as well. So you can check that out. And we have a public version, so you can explore that as well for limited number of models. So yeah.
Sure. Thank you so much, Pratina, for that insightful presentation. We are now opening the floor to the questions, and to that we have a first question from Avinish. He says, "What is our advantage vis-a-vis competition in this?"
Okay, so cool. So again, advantage is something like, okay, you are actually able to derive explanations which are reliable. It's not like LIME or SHAP, which is just based on surrogate modeling. You have something which is much more deterministic. You are actually able to explain the regulator how the explanations are coming. And with this, you can actually ensure that the model is whenever you are saying this, you have a proper explanation to the model prediction. So it's not like black box and similar to, I would say, Lyman Sharp. You can actually have certain basis of your explanation, which through which you can actually satisfy the regulators' expectations, I would say. So yeah.
Sure. The next question we have is what strategic advantages does DLBacktrace offer over traditional interpretability techniques like SHAP or LIME for high-stake domains like finance and healthcare?
Sure. So with finance and healthcare, again, both of them are, I would say, quite similar because again, the stakes are very high for both of them, and you cannot have any, I would say, unconfident or unexplainable model in it. You have to be very trustworthy. So with Lime and Sharp, the problem is again, there, I would say there's something called surrogate modeling. Basically, you just see the input and the output, and based on that, you try to create explanations. The problem in that is you have something called scaffolding attacks through which you can fool these methods, and hence a lot of regulators are actually not very confident on these methods, and hence I would say there this creates a problem when you are actually trying to justify your model decision. So that's where the DL backtrace actually came to the picture because again the reason why we worked on this is because we also had a similar issue, and hence we try to work on a solution which can be deterministic. It cannot be fooled by just scaffolding attacks or perturbation based attacks, and it can actually be deterministic and explain to a regulator how the even the explanation or the decision is being made. So yeah.
Sure.
Cool.
Uh, Thank you. Next question we have is it possible to do this affordably for large models and, for example, ChatGPT? And how long does it take test on ChatGPT for the example that you've showed?
Okay, sure. So right now, I would say for ChatGPT, the thing is it's like a closed source model. You don't have the model weights or API, so you cannot actually do anything with ChatGPT. But you have Llama and MOEs, which are, I would say, open source. You have the model weights available on, I would say, Hugging Face. So with a Llama model, I would say right now we are trying to reduce the speed, but like basically increase the speed of how we are doing this. Um, you can do it in like I would say a minute or two right now, but uh, right now we are also increasing the capabilities of optimization. So it will in I would say next few months it will reach to similar to your inference timing, like how much time it takes for your inference, similar extra time you would require for the explainability part. So yeah, and we are also exploring how you can do it hand in hand with inference so that you're not actually doing it, I would say, wasting resources on this. You can actually do it in a single go. So that is few things which we are exploring. But yeah.
Sure. The next one we have is are the relevance scores computed independently for each layer, or is there a layer-wise dependency? I'm assuming that there needs to be a layer-wise dependency for this method to be architecture independent.
Okay, so yeah. So with the relevance scores, again, you are computing it for each layer. I would say it for each operation, similar to your model, like where you actually go through certain layers and you have certain operations. So we try to compute the relevance for each layer and operation, and hence you get the relevance value for each layer and operation. However, the thing is, when you're doing this, you're also getting it neuron wise. Okay, so when I say that is, it's similar to your input features, you're getting the relevance values, and hence you can use these uh, to basically do all this tasks which I was mentioning. But again, there is a dependency a bit for the layer wise thing, but with we are covering all the layers which are there in PyTorch. So it will cover like most, or I would say 90% of the models which are being developed in today's world. If in case someone is doing like a very custom model from scratch, then it creates a problem. But apart from that, I would say 95% of the models will be covered with the library which we have internally. So yeah.
Sure. We missed a question from Daniel. So how
Mhm.
does this compare with SAEs and what about the scalability? SAEs have been extremely compute intensive to train for large models.
Sure, that's an interesting question. So with SAEs, I would say there's a mixed opinion with everyone in the industry, especially mechanistic interpretability, I would say. So with essays, as again rightly pointed out, it takes a lot of time, and again it's very computationally expensive. But with backtrace, that's not an issue. You're not training anything. you already have your pre-trained model. What you're computing is just the relevance or the explainability for your particular instance. So it's not, I would say, compute expensive as essays. It's more just on the inference side, whatever you are computing, and it can be scaled really well, I would say. It's just based on whatever model you are using. So yeah, and compared to essays, I would say it is um, much more better if you're thinking of scalability, because with essays, every time you need to train a new essay for a different model. But with this, it's just not training anything, you're just doing inference. So yeah.
Right. Another question we have is, how does DLBacktrace help assess and mitigate the risks of hallucination or token level failures in generative models?
Okay, sure. Again, that's again an interesting question. So that is something which we are testing out right now, because you have all these layer-wise relevance and importance which you are getting. So once you have all these importance, you are actually able to understand how your model is actually functioning. So with this, what you can do is, again, you can find out areas of your model which is actually, I would say, the values which are increasing, I would say, unconditionally or unexpectedly when you are, let's say, hallucinating a particular token or when during prediction. So if you are able to observe that, and hence you are actually able to understand when the hallucination is happening, so you can get like token level failures. Similar thing, which is something which we tried on the optimization front, I would say, especially for different models, and that is something which we saw. There is a pattern between the backtrace explainability which you get and certain predictions, and through which we have a few results which are good for pruning. But this is something which we are currently exploring, and I think few months you will get some results from us. So yeah.
Right. These are some great questions that we have.
Mhm.
We have another one. Is backtrace similar to LRP? I believe LRP also give relevance for LLMs.
Okay, okay. So with LRP, the thing is you have certain rules. So again, that's correct. You in LRP also you get relevance, but in LRP the problem is, again, you have certain rules for different layers. So you have to choose again which rule you want for certain layers to make it actually work well. Whereas in our case, you have a single logic for all the layers. So you are just single logic which you are using, and hence you don't have any configuration which you have to configure for different models. You just do it on the inference level on a single scale. And with LRP, again, the problem is again scalability. While LRP has been there for a lot of years, the scalability is the issue. Because with LRP, since you're doing different rules for different layers, you have to select that, and in order to do it in a scalable manner is something which is very difficult. Where in our case, since we already have just one singular rule for default mode and one for contrast mode, you can scale it effectively and you can do it in a single manner. So yeah.
Right. And yes, we have another one from Jatin. How to choose between the two modes?
Okay, yeah, interesting. So with two modes, again, when you're doing a normal task, let's say you just want normal explainability, you can just go with the default mode. It's pretty straightforward. Whereas for contrastive mode, you are actually trying to distinguish why and when your model is making certain decisions. You prefer to go into contrastive mode. Again, in some of the results which we tried out for the experiments, we just showed for default mode. But for contrastive mode, in sometimes the results are actually better because you are actually just getting positive contributions for the decision being made. So again, it depends on your use case, what you're actually focusing on. But yeah, like in most cases, default mode is good. But if you're using something which is very much focused on just the accuracy, yeah.
Right. Um, if we have more questions, we can, we have a couple of minutes. Feel free. Yep, we have another one from Daniel. Can we use backtrace for factuality correlation to neurons, like what Anthropic done using SAE on LLMs?
Okay, that is something you can of course try it out. Again, with the open source version, that is somewhat limited, but the closed source version, yes. So you can try out something like that. Of course, with Anthropic, since they're using sparse autoencoders, it takes them a lot of time firstly to train those sparse autoencoders and then do this factuality correlation. Whereas for backtrace, I would say again, you can do it fast, but again, you have to do factuality correlation can be a bit hard because we are following a relevance-based approach. So you're while you are getting relevance for each particular neuron, that is a bit different from what Anthropic is doing with sparse or trend coders. So yeah, like in short, you can do it, but the approach will be a bit different. So yeah.
Sure. Thank you. I think we still have a few minutes before we close. If you have any questions, please feel free to drop them in the chat box.
Yeah, actual limitations.
Are there
Okay.
any architecture limitations where DL-backtrace won't work? For example, does it require Montic or smooth activations?
No, okay. So with DLBacktrace, that's not an issue. So if you have seen the open source version, you can, if you are, let's say, using a custom activation function, or yeah, you can use any sort of activation function. The only thing is you have to just define it correctly. So that's not a problem. Architecture limitations, I would say, in most cases, it won't be there unless and until, let's say, you're using a custom CUDA layer that is like extremes in optimization. So in that case, it can be tricky to incorporate that. But if you're using a normal models and where you're using PyTorch layers, in which is 95% of the cases, it will work. So that won't be a problem. So yeah. Okay,
Sure.
next question. Qualify
Is there
explanation
a
method
way
as
to
well.
quantify these explanations between methods, like how MPRT been used for LLMs?
Okay, cool. So yeah, you can use the different explanation like quantifications. So we also have a library called AryaXAI evals to quantify different explanation methods. We used MPRT for we didn't use it for LLMs. We use it for MLP, but you can also use it for LLMs as well. The only thing is, um, again, the thing is for different methods and tasks, it's something it has been underexplored, I would say. Hence, there are very few libraries which actually work around this. So similar to what we have XAI evals, which are open source. So yes, you can, in short, you can quantify between these methods, and you can use something like MPRT, which can be universal. You can make a method of your own. So that is also something which you can do and contribute to open research. So yeah.
Yep. And we have another question. Are there any opportunities for students to be a part of your research work or projects?
Yeah, of course, like we do hire a lot of, I would say, students. We have a few interns I would say, last 6 months who have been working around these themes around AI alignment, how you can use DL backtrace to have actual insights. And we have a lot of stuff around, I would say, explainability. So, of course, you can, I would say, reach out to me or the team, and we can move forward from that. We are very open in terms of research. We try to publish at least one publication per intern or a student. So yeah, feel free to reach out.
Great. I think we've had a bunch of really nice and interesting questions. And if you still have any questions, please feel free to send them across and we would love to address them. And I think that brings us to the today's webinar, end of today's webinar. And thank you once again for joining us. We hope this gave you valuable insight into DL Backtrace and its potential to bring transparency and trust into deep learning systems, from standard architectures to large language models. We will be sharing the recording of the session soon with all of you. And if you'd like to learn more about AryaXAI or get involved, please feel free to check out our website. And you can also connect with us on LinkedIn. Thank you so much once again, and we look forward to seeing you at the future sessions. Take care and goodbye. Thank you.